Hi students, welcome to physics class. In this video, we will discuss about simple pendulum and we will show that the oscillations of simple pendulum are simple harmonic. Let us start with the definition of simple pendulum. A metal bob suspended by means of massless, torsionless and inextensible thread is called as simple pendulum. The diagrammatic representation of simple pendulum is shown in the figure. Let us redraw this simple pendulum. The one end of thread is suspended to a rigid support and another end is connected to a metal bob. This system is called as simple pendulum. Next, we will try to know what is the length of the pendulum. It is defined as the distance between the point of suspension and center of the metal bob is called as length of the pendulum. Here S is the point of suspension and this point is the center of the bob and the length is called as the length of the pendulum. Now coming to the detailed explanation of the figure, we have taken a rigid support here and S is the point of suspension, and when the pendulum is at mean position, that is at the center, that is at rest, there exist two forces acting on the pendulum, that is the tension T1 and the gravitational force mg. Now from the figure, T1 is equal to mg. This is the equation 1. Here T1 is balanced by the gravitational force at the mean position. T1 is the tension in the string. Now oscillate this pendulum with a very small angular displacement theta, and while the pendulum is oscillating, we will try to observe the forces acting at the extreme position. Similar to the mean position, at extreme position also there exist two forces acting on the pendulum. The first one is mg, the gravitational force acting downwards, and the second one is T2, the tension acting towards the point of suspension as shown in the figure. At this extreme position, T2 and mg are not balanced by each other, so we can resolve the gravitational force mg into two orthogonal components. They are A, mg cos theta and B, mg sin theta. After resolving mg into two components, the T2 is balanced by mg cos theta, so we can write the balancing equation T2 is equal to mg cos theta. Next, coming to the other component mg sin theta, which is unbalanced, so we can write the unbalanced force is equal to mg sin theta. Now observe the figure carefully. Mg sin theta and y are acting in opposite direction. Here mg sin theta is responsible for the acceleration of the metal bob or the pendulum and y is the displacement of the pendulum. Next, coming to the equation, we can write the unbalanced force F is equal to mg sin theta. From Newton's second law, we can write F is equal to ma, which is equal to mg sin theta. Here m gets cancelled, therefore a is equal to g into sin theta. As theta is very less, that is the angular displacement of the simple pendulum is very less, then we can write sin theta is approximately equal to theta. In order to show the oscillations of simple pendulum or simple harmonic, the angular displacement of the pendulum must be very less. If the pendulum has larger angular displacement, then we cannot observe the simple harmonic motions in the pendulum. So again, coming to the equation part, the acceleration A can be written as g into theta. Now again, coming to the figure, this portion of the figure is similar to the sector, so we can write arc length is equal to radius, which is here the length, and multiplied by the angle, here the angle is theta. Therefore arc length y is equal to L, the radius, into angle theta, and finally we obtain theta is equal to y by L. Now by substituting theta value in this expression, we obtain A is equal to g into y by L. Here we can write minus here because the acceleration A and y are opposite to each other, as we have discussed in the starting. This same expression can be written as A is equal to minus g by L into y. By comparing the above equation with A is equal to minus omega square y, we get omega square is equal to g by L. Therefore omega is equal to square root of g by L. The acceleration of simple pendulum is similar to the acceleration of simple harmonic motion. So we can say that the motion of simple pendulum is simple harmonic motion. Now we will define the time period of simple pendulum. The time period is defined as the time taken for one oscillation, that is the time taken by the simple pendulum to complete one oscillation is called as time period. The time period can be represented as t is equal to 2 pi by omega, which is equal to 2 pi by omega means we have already derived square root of g by L. Therefore the time period of simple pendulum t is equal to 2 pi square root of L by g. Next we will define seconds pendulum. Seconds pendulum is defined as a pendulum whose time period is equal to 2 seconds is called as seconds pendulum. That is, time period t is equal to 2 seconds. Now we have to find out the length of the seconds pendulum. We know that the time period t is equal to 2 pi square root of L by g. Next, by squaring on both sides we get t square is equal to 4 pi square L by g. Therefore L is equal to t square into g divided by 4 pi square. Now by substituting the corresponding values, we obtain the length of the seconds pendulum as L is equal to 1 meter or 100 centimeters. Thank you.